Number 4 brings us back to one of the tests that we haven't seen that much of. So if you first look at it, you see, oh my goodness, we have 2 different methods, and we're looking for significant difference, providing statistical justification. So hopefully we're already thinking maybe a 2-sample t-test for means. Looks like we have quantitative data, they've mentioned the word means, and we have 2 groups. Now, if we read a little bit closer though, I'm hoping that as you guys did this problem, you recognized that these methods did have a meaningful way to pair them. Each one of these methods was done on a specific specimen. So they have each method on the same particular piece of beef. So we definitely have a meaningful way to pair this data up. And the fact that we have the data in a line like this with them nice and obviously paired should hopefully have been an indication of this. So what we're doing is actually going to be a paired t-test for a mean. You don't necessarily need to call it a paired t-test. But we are looking at a paired t-test. So this one we haven't seen very often, but typically first thing we want to do is establish what our ho and ha are. In this case, our mean, our null hypothesis is the mean difference is equal to 0. And our alternative is that the mean difference does not equal 0. And that's because we don't have anything here saying we think one is going to be show more contamination than the other. And of course we need to define what that mu d equals. This is going to be the mean difference between method A and method B in terms of contamination. Something like that. We definitely want to mention that this is about contamination. Oh my god, I'm going to have to steal how to spell that because I can't do it. Oh, good, no wonders. Contamination. Oh my god, it's getting worse. Got it. Third try. The charm. The most important thing here is that we're talking about just a single mean, and it's the mean of the differences. So if we went one step further, what this table should have had, and I don't expect them to do this to you guys on the test for this year, but they should have had an A minus B row where we could have seen this one was off 0.3, this one was a positive 0.4, positive 0.3. I can't do this math in my head right now, but you guys hopefully can see where I'm going here. It looks like typically method A is giving higher values than method B, though there are a couple of exceptions, right? But for the most part, method A's value of contamination is higher than method B's, with specimens 1, 9, and 10 showing some sort of difference. So we got our hypotheses. We should probably mention what we're doing in terms of a test. We don't really need to say paired test. If you did, awesome. But technically, this is really just a t-test for means. That's all it is. We're just making a special new variable before we begin. So this is a t-test for a mean. That's all it is. If you put paired t-test, even better, but we're just looking at one particular set of data, one sample of 10, and doing that. And now, before we go calculate anything, we should be checking our conditions to make sure that they're satisfied, right? So our big 4, obviously my usual independence comes from the big 3 that are on the AP all the time, but the big 4 that I like to have are 1, a simple random sample, 2, independence. This is the one that AP typically does not actually assess. It's sort of just given from the other 2. 3, N is less than 10% of the population. And then 4, that either, basically our normality assumption, which means that we either have our original thing was normal, or N is greater than or equal to 30. And so for this last one, we already know our N was only 10. We only had 10 specimens, so we're looking for normality in the original. Listing them is not enough for checking conditions. We got to make sure that we showed how we met them. So for SRS, we're looking up here. We see randomly selected specimens, so we'll just write that down in some quotations. Randomly selected. And then we will go ahead. I even like going ahead if you can. We don't have this beauty on the AP this year, but saying it says randomly selected, so stated, and a check mark. Independents, if they're randomly selected, we should be good. N is less than 10% of the population. You would just want to say that there are definitely more than 100 cuts of meat. Right, we have 10, so that means our population must be at least 100. Sort of arbitrary. I doubt they wouldn't actually assess this one. Normally they assess ones that are pretty obvious. And then last one, did they tell us something about normality or n being greater than or equal to 30? And if we look up, doesn't look like they said normal. We definitely don't have n is equal to 30. So this is the one that Schiffer had asked me to go through and say, how would we do this? And it's the one that Professor Rossman had shown in his slide as well. Since we can't say this, we need to look at the sample and basically show that our sample is not super screwed up. There are no huge outliers. So typically what this would require is maybe a dot plot. That's the simplest thing that we can do on our own. Now, I don't believe they'll make you do this on the AP. There's been a lot of like explicit statements that you're not gonna have to draw any graphs since so many students might be typing things in with their computer. But we'll go ahead and do it just because we're at this. Since we're looking at differences as our thing, that's what we're going to make our little graph for. So -1, 0, 1. I'm making a real ghetto graph. I'm just trying to get this thing done. So we have 1 at -1, -0.3, 0.5, 0.3, 0.6, 0.8, 0.7, 1.2, 0.2, -0.1, and 1. And so you might say, -1 might be an outlier. And this is where I think it was Hydorn who asked, can we just say proceed with caution? Because that's like the go-to AP stats thing. So this is definitely a little sketchy in terms of whether or not we can continue, because this one does seem pretty far away from the others. Our next -1 is that -0.2. So we are definitely going to say proceed with caution. If you wanted to continue, you probably want to say it's not that far away. We're going to go ahead anyways and just assume it's not an outlier. It's a pretty small sample size. So at this point, we would then do our t-test in our calculators, using those differences as our actual values, giving out our t and our p-value, and continuing on from there. So I don't expect us to need to do this. I will just go ahead, since we have this problem, I will do it all the way through for you guys for completeness. So you'll see here, your calculator, no paired tests. There are paired tests and things like StatCrunch. We don't have one. So we just need to put in the actual differences into our t-test. So stat, edit, clear out my L1. This is when I'm not totally comfortable with my ability to do math. And I think I might have some errors there. I might use L1 and L2 and enter the actual values to verify as I went. In fact, I can actually do each of these, 22.7 minus 23. I get the first value. Continue on. I'm going to trust my math, even though I'm not feeling the most confident with my math skills at the moment. It is Sunday afternoon, so who knows. But I'll just put them in. 0.2, -0.1, and -1. So we got all 10 of them in. We don't necessarily need to deduce the 1-bar stats. I like to do it just for like my own edification to make sure it makes sense what I got out. My X-bar here looks like 0.29. So as we see, most of them were positive. It makes sense that method 1 is showing more contamination. And S, 6.3-ish. Or 0.63. I don't need to actually write them down because when I go into t-test, my calculator will autofill them. It is super smart. And we're just looking at whether or not this difference is 0. So is 0.29 so different from 0 that we can conclude that there's a difference in method. So we get out a t of 1.45 and a p-value of 1.79. 1.793. And they didn't give us a significance level, but they don't need to when our p-value is this bananas. This is greater than any alpha we might want to use. I suggest just sticking with that 0.05. You're never going to get in trouble with that on the AP. Just to verify, yep, they didn't tell us. And so since the p-value is greater than alpha equal to 0.05, we fail to reject the null. There is not enough evidence to conclude. And then I'm going to do my nice lazy thing. I'm going to grab a significant difference in blah, 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 blah. I'm just going to steal all of that and write it at the end of there. Then talk you through the rubric. Here it is. You can see part 1, you got to state the hypotheses. You needed that mu d equal to 0 or not equal to 0, and then to specify that's the mean difference. Part 2, to name the test or put the formula. Name is perfect, so that t-test for mean is great. And to test our conditions. And so in this case, the only thing they have is that we have randomly selected, so it's possible to say they're independent, and the population are normal, and they go ahead and give us this lovely histogram of differences, which is the same thing as our dot plot, right? It's symmetric, no apparent outliers. Even though it's hard to judge, it appears normal reasonably. Like I said, they're typically very generous. You need something really egregious to say it doesn't follow this normal distribution or it violates that assumption. Mechanics-wise, it looks like they wanted the value of the test statistic. That's my t. We got that. And our p-value, we got that. I didn't write down the degree of freedom, so right now I'm looking a little sketchy. I probably didn't get an E for part 3. So just note, if your calculator pops out a degree of freedom, oh, mine did not. Apparently I should have given that, so we'll see. Conclusion, since it's greater than 0.05, we cannot reject. We do not have statistical evidence to show. Yada, yada, yada. So let's just look really quick at how these things were scored. Part 1, the correct pair of hypotheses. May be stated with a mu A and a mu B. I'm confused by that, but okay. Part 2, essentially correct if they identify the test and check the appropriate conditions. Interesting. So not acceptable to say there are 20 observations there since there's only 10. That's fine. So if you use 2 different samples, you lose this as incorrect for paired. And then graphical check of normality is required for this one. Like I said, they said no graphs, but we're still good there. So they showed a box plot, they showed a normality plot. They actually didn't show a dot plot, but that's what they typically have used on the current tests. It looks like you're essentially correct if you have mechanics with a test statistic and p-value. So it did not actually have degree of freedom in that requirement. Hooray! And then essentially correct for the last one. You basically needed a linkage of why alpha and p-value were given, and then the actual conclusion, which we knew about. So nothing really surprising there in terms of that test. It's not a test we've done really often, which is why I wanted us to see it again. We've only seen that paired test like once, so I wanted us to get one more chance at it. I do not think they're going to walk us through a test like this. I think if anything, they would have us set up this first step, the hypotheses with the name, and then they might have us check assumptions or discuss why assumptions are important, and then they will have us talk about this conclusion. I do not think there's any chance, I mean, I could be completely wrong, of having us use the calculator stuff, because it's just plug and chug, and at this point, that wouldn't be different for any people, for all the different students. So I do think that we're probably looking at, hypotheses, conditions, and then maybe that definitely that conclusion from a given p-value.